In this video, we'll explore sampling distributions. Suppose we're interested in some broader population of interest, where the behavior of the individuals in the population can be described by some underlying probability model. To learn about this population, we need not observe every individual within it. Rather, we can use data on a sample from that population. It turns out that these data points are observations of random variables sampled from the underlying probability model. Thus, we can use our understanding of random variables to understand how our data might behave. Let's focus on the samples here. In general, let x1, x2 up to xn denote a set of measurements or data taken on a sample of n objects. For example, the x's might be the heights of n sampled adults, or the number of customers on a sample of n days. Then we say that these xi are independent and identically distributed, IID, or equivalently that the xi are a random sample if they satisfy two conditions. First, independent means that the xi are all independent of one another. Second, identically distributed means that the xi are all drawn from the same population or probability model. This means that though the eventual outcomes of the xi might differ, they all have the same underlying properties. For example, all xi have the same PDF or PMF, the same CDF, the same expected value, variance, moment generating function, and so on. Consider an example. Suppose we're interested in the heights among the population of all adults, where these heights roughly follow a normal model. To learn about this population, we take a sample of just 20 adults and record their heights, x1, x2, up to x20. Assuming that these 20 adults are randomly selected, for example through a random drawing, then these heights xi are IID. Specifically, the height of any one sampled adult is independent of the others. Further, the adults are all sampled from the same underlying population or probability model, thus are identically distributed. In contrast, if our sample of 20 adults consists of 10 pairs of twins, the xi are not IID. Specifically, since the pairs of twins are biologically related, the height of one twin is not independent of the height of the other twin. As another example, consider a uniform 0-1 random number generator that can be used to generate numbers that are equally likely to be anywhere between 0 and 1. Further, let x1, x2 up to x5 denote an IID sample of 5 random numbers. Thus, each xi has a uniform 0-1 model. Let's explore how this sampling might play out in practice. Shown here is just one possible sample of 5 uniform 0-1 outcomes, listed and plotted below. Notice that among this sample, the minimum value is 0.00802, the maximum is 0.879, and the sum of these 5 sample numbers is 1.88. Of course, if we take a different sample of 5 numbers, the sample values and their summaries both change. In this second sample, the minimum value is 0.0219, the maximum is 0.888, and the sum is 2.75. We repeat this process over and over, in all obtaining 1,000 separate samples of 5 uniform numbers each. The important thing to note here is that not only do the values vary from individual to individual within our samples, the sample statistics or properties vary from sample to sample. The messy plot here exhibits the 5 sample outcomes on the x-axis for each of the 1,000 samples on the y-axis. For example, the 5 dots at the very top of the plot with y equals 1,000 represent the 5 data points in the 1,000th sample. The yellow dots here represent the minimum outcome in each sample. Notice that these are not uniformly distributed between 0 and 1. They tend to be closer to 0. This makes some sense because these are the smallest numbers in each sample. More specifically, the histogram here represents how the sample minimums vary from sample to sample. Most of the sample minimums are under 0.25, and almost all are below 0.5. Similarly, consider the maximum outcome in each sample. These are also not uniformly distributed between 0 and 1. They tend to be closer to 1, as they're the biggest number of the sample. Specifically, most of the sample maximums are above 0.75, and almost all are above 0.5. Finally, we can take the sum of each of our 1,000 samples. Since each sample consists of 5 values between 0 and 1, the sample sums range between 0 and 5. Further, the sums are more likely to be close to the middle of this range, 2.5, than to the edges. And this makes sense. For example, for a sum to be closer to 5, it would require that all 5 sample values are close to 1. Stepping back, this simulation reflects some important themes in random sampling. In general, we can summarize the behavior of an IID sample, x1, x2 up to xn, using simple summary statistics, such as the sample minimum, maximum, sum, and mean. As we observed in our uniform simulation, just as the individual x values can vary from individual to individual, these sample statistics can vary from sample to sample. For example, not every sample has the same minimum outcome. This means that these statistics, which are computed from random variables x, themselves are random variables. Thus, these sample statistics can be described by their own underlying models. These models are called sampling distributions. Specifically, unlike the population model, which describes how the individual xi can vary from individual to individual within the population or sample, a sampling distribution describes how a sample statistic can vary from sample to sample. For example, in our uniform simulation, the behavior of the individual sample outcomes are represented by the uniform population model, whereas the behavior of the sample minimums is described by an underlying sampling distribution. And thus far, we've only simulated or approximated the sampling distribution of the sample minimum, maximum, and sum. And we've done this in a specific uniform setting. However, we can also build the complete, not just approximate, sampling distributions for sample statistics. In general, let x1, x2 up to xn be an IID sample from some population. Thus, the xi share some common PDF little f of x, a common CDF big F, and a common moment generating function m of x. Further, let x min, x max, and x sum denote the min, max, and sum of the sample. Then we can build the sampling distributions or models of these sample summaries. First, when our xi are continuous, the PDF of their minimum value is the sample size n times the common PDF little f times the quantity 1 minus the common CDF big F to the power n minus 1. We can also build a formula for discrete xi, but won't do so today. Similarly, when our xi are continuous, the PDF of the maximum value is quite similar to that of the minimum value, with the exception of the CDF-related term here. Finally, for reasons that will be more clear once we start applying these results, moment-generating functions are a handy tool when summarizing sums. To this end, the MGF of the sample sum, x sum, is the common MGF of the xi to the nth power. Notice that though these sample models of the sample summaries vary depending upon whether we're modeling the sample min, the max, or the sum, notice that they each depend on both the models of the individual sample values through their PDF, CDF, or MGF, as well as the size of the sample, n. Though the general results are nice in that they can be broadly applied, they're quite abstract. Let's apply them in our uniform 0-1 sample setting. Since our 5 sample values, x1 up to x5, are all drawn from a uniform model on 0 to 1, each individual xi has the PDF and CDF shown here. Consider the minimum of this 5-number sample. To obtain the PDF of xmin, we can utilize the general formula on the previous slide and plug in our context-specific information. In particular, we can plug in 5 for our sample size n, x for the CDF big F, and 1 for the PDF little f. Simplifying things, the PDF of xmin is 5 times 1 minus x to the 4th for x in 0 to 1. Similarly, plugging into the general formula for the PDF of x max on the previous slide, the PDF of the maximum of our uniform sample simplifies to 5 times x to the 4th for x in 0 to 1. Stepping back, we started with a uniform population model which describes how the xi values can vary from individual to individual in the population, hence in our sample from the population. In this example, each individual xi value is equally likely to be any value between 0 and 1. We then built the models of xn, xmin, and xmax, the PDFs of which are plotted here. Whereas the population model describes how the xi values might vary from individual to individual, these sampling distributions describe how the minimum and maximum of the sample vary from sample to sample. That is, not every sample will have the same min and max values. In our example, the PDFs illustrate that the minimum of a uniform sample is more likely to be close to 0 than close to 1, and the maximum is more likely to be close to 1. And these theoretical results are similar to their approximations that we obtained from our earlier simulation. Finally, we can use our general results to build a model for the sum of our uniform sample. In this case, we need to utilize MGFs. To this end, the uniform 0-1 model, hence each xi in our sample, has the following MGF. Plugging this into our formula from the previous slide, the sum of the uniform sample has MGF e to the t minus 1 divided by t, all to the 5th power, where 5 is our sample size. As it turns out, this is not the MGF for any common probability model. That is, it doesn't turn out to be the MGF for a normal or a gamma or a uniform, meaning that the sum of a uniform sample is not itself uniform or normal or gamma, or again, anything else that is familiar to us. And this observation is consistent with what we observed in our simulation of the sample sum. Mainly, the sum of a sample of 5 uniform 0-1 values is not equally likely to be any number between 0 and 5. It's more likely to take on values near the middle of this range. In conclusion, in this video we've simulated and applied sampling distributions for the sample min, max, and sum. In the next video, we'll formally prove or build these models.